Okay, so chapter 11, systems of equations. Mostly kind of review for you guys, not too much new in here. The first section just reviews how to find solutions of your basic linear systems, which we've sort of been doing throughout the year, here and there. And we'll start with some pictures. If you remember anything from algebra, which you probably do, you're probably used to seeing these pictures. Okay? This represents a system with what? You guys remember? Parallel lines, which means no solution. Very good. We call this inconsistent. This represents a system of equations with, well, maybe perpendicular, not necessarily. Intersecting, so how many solutions? One solution. We call this consistent and independent. Something that's inconsistent does not have a solution. Something that is consistent has one solution or possibly more. This is an example of two equations that are really, what? Overlapping. So how many intersection points are there? Good. So there's infinitely many answers. This is also consistent. But now we just call it dependent. Okay, and I'll go ahead and put a little box around this scenario because we are going to go a little bit more in depth with this kind of situation. And we'll get into that a little bit more tomorrow. Okay? But the rest of this section, I mean, honestly, it's pretty easy. So there are three methods that you should be comfortable with for solving systems. We're going to learn a couple others, but three that you know so far. One of them is graphing. Which entails what? Graphing it and what? Finding the intersection, okay? So you graph both equations, find the intersection. You can either do it by hand or on the graphing calculator. You guys know how to do that. Then you went ahead and learned about substitution. Which meant that you isolated a variable in one equation and then you plugged this in to the other equation. And then you solved. Third, which is probably the most convenient but often the most forgotten, was the addition or elimination method. in which case you multiplied one or both equations together. And then added them to cancel one variable out. Do these sound familiar? Okay. So here's what we'll do. I will do a couple of examples with you guys. I'll give you a minute to kind of work through it, and hopefully we all arrive at the same answer. Let's try using substitution with this one. Yeah, that's a 4. Okay? So substitution. First, we try to get something alone, which we already have, right? So now what can I do? Plug what into where? So plug this equation into second one. Faux show indeed. 5x plus 2, what's y? 3x minus 4. That equals 7. If you combine your like terms, you have 5x here, 6x there. That's 11x minus 8 equals 7. Add 8. 11x equals 15, so x is 15 over 11. Okay. Once I know what the x-coordinate of the intersection is, what could I do to find the y-coordinate? Plug it into where? Yeah, the purple one's easier. Does it matter which one we do? Really, it doesn't, but I mean, here y is already alone, so it makes much more sense to go there. So if I plug it into the y equals 3 times x equation, we're going to plug in x, which is 15/11, subtract 4. We get 45 over 11 minus 4. Uh-oh, running out of ink. 45/11 minus 4 is 1/11, I believe. What's that? Yes. Okay. So here is our solution. Solution is the ordered pair 15/11, comma 1/11. Yes, because you are finding the intersection point. How do we check to see if this is correct? To where? Well, there's two of them, right? This is the point I want to make. If you want to check to see if your answer is correct, you plug in x and y into both equations to make sure they work. Okay, so even if it works in one, okay, you may have made a mistake somewhere and it may not work in the first one. Okay, so very good to make sure that you understand it's got to work for both equations in order for it to be a solution. Looks familiar? Are we good? Going too fast? Isaac clearly thinks I'm going too slow. Okay. Let's try this one. 3x plus 5y equals 7. 2x plus 3y equals 4. And with this one, let's use the addition or elimination method. You guys remember how elimination works?
Yeah, you gotta get either the x or the y the same.
So either the x or the y, the same number?
Yeah.
Okay. I guess I should clarify. We could add or subtract the equations. It doesn't make a difference. If we're going to stick with addition, though, we don't want them to be exactly the same.
Opposite.
We want them to be opposites, right? So let's say I want to work on the x's. Yep.
Is this one where it's like multiply it and get this?
So what would I multiply here by? If I want to get the x's to drop out. What is it? 2. And let's do one of these negatives so that they're opposites. Well, do you want to do subtraction? Okay. No problem with me. So we get 6x plus 2 times 5 is 10y. 2 times 7 is 14. Double the second equation, we get 6x. I'm sorry, not double, triple it. Plus 9y equals 12. And since we have exactly the same, if I want these to cancel out, I don't add, but I subtract the equations together. So 6x minus 6x is equal to 0. 10y minus 9y is just 1y. And then 14 minus 12 is 2. So here we have that y is equal to 2. And now to find x, plug 2 into, and here you just make a choice. I'll go with the second one. So if I plug it into the second equation, we have 2x plus 3 times y, which is 2, equal to 4. That's 6, so 4 minus 6 is negative 2. Yep. Technically, it doesn't matter. It could be in any of these 4. But I always would prefer and ask you guys to do the same, to go back to one of the originals, because this was given to you. Here you did something to it. It's possible that you might have done something incorrect. But I mean, if everything's correct, it shouldn't matter. That's a good question. What's x then? X is negative 1. So our solution here is negative 1 comma 2. Make sense? Sometimes if you hear at the same time as you see, it can, you can tell what my scribbles are.
I'll try that Monday.
Okay. Sorry about that.
It's fine. We all make mistakes.
All right, so are we good? I mean, you guys understand graphing, substitution, elimination? Okay? So what I want to spend the next couple minutes doing are some of the applications. So, I mean, back in Algebra 1 and 2, this might have been a whole unit that we're doing in 20 minutes right now. But here are some application problems. Let's do an algebraic one. Determine constants. Oh, let me switch back to black ink here. B and C such that y equals x squared plus bx plus c passes through the points negative 3, 1 and negative 1, negative 2. So I mean, the point of application problems like this is it doesn't start out as a system, but once you get started, it eventually turns into a system of equations. Okay, so what I'm trying to do is find B and C. What are you guys inclined to do here?
So,
How?
B
Yeah.
and
How?
C, the numbers.
Which numbers?
Uh, 3
Good idea. So let's take this point, plug it into the equation here, see what happens. What's y?
and 1.
So we're going to plug this in. We get 1 equal to x squared becomes 9 plus b times x, which is negative 3, plus c. And then I'm going to clean up the equation a little bit. If I subtract 9, I get negative 8. B times negative 3 is just negative 3b plus c. So now how do I find b or c? Do another one. Yes, that's why they gave you 2 points. You have 2 variables. You have 2 points you can plug in. That's how we're going to get down to finding the 2. So now we plug negative 1 and negative 2 in. So that becomes what? Yep. Equals, what's x squared? Plus b times x, negative 1 plus c. Clean it up. Subtract 1, we get negative 3. And then that's equal to negative b plus c. Unless you want me to, I don't need to keep going. I think the point is get to a point where you know what to do, right? Do you guys know what to do from here? What's one thing you can do? So maybe solve for c up here, and then plug it into the second one. Or elimination. You could just subtract right away, right? If you subtract right away, c minus c drops out, and then you get your answer for b. Okay, so we good with that? All right, another application. We'll set it up, and we'll leave the solving for you guys at home. Let's say we have 2 acid solutions. That's what I said, yes. And let's say A is 20% acid, so that's the concentration. Let's say the solution from B is 45%. And here's the question. How many, let's say, mLs from each solution do you need to create a solution of 100 mLs with, let's say, 30% acid? Again, it's not your run-of-the-mill, here's one equation, here's another one, find x and y, but eventually it turns into something like that. So can we write 2 equations? What's one? Well, let's say, what is A going to represent?
20%.
A equals 20%. Is that what you mean? Okay. Obviously, you guys know what to do. I just want to make sure we understand what the variables represent. A represents the number of milliliters from A. Does that make sense? I mean, look at the question. We're looking for how many milliliters from each solution. So naturally, our variables should represent milliliters from first container and number of milliliters from second container. Okay, and one of you already said the first equation, which is what? A plus B equals 100. See, now this makes sense. The amount of milliliters from A combined with the amount of milliliters from B should add up to the total, which is 100 milliliters. Okay? So this is your first equation, which purely represents how many milliliters we're talking about from each container. Second one, we're going to use the concentration. In other words, the amount of acid. So the first equation represents quantity. The second equation represents a slightly different quantity. It's the amount of acid in the containers. What is it? Okay, well, think about what the 30% means. That when I'm done, 30% of my 100 milliliters should be acid, right? In other words, 0.3 out of the 100 is what I should end up with total. Does that make sense? And I mean, look at the pattern here. Percentage, amount, right? Percentage times amount. That's exactly what we should do on the left. What's the percentage from A? So it'll be 0.2, and then here's our amount. Our amount is whatever A is, right? What's the next term? So first equation represents the total number of milliliters. The second equation represents the total number of milliliters that are acid. 20% of the ones that come from A are acid, 45% of the ones that come from B are acid, and then in the end, 30% out of the 100 are acid. Does that make sense? Okay. A common mistake that I see here is people forgetting this 0.3. Or I'm sorry, the 100. And they just do 0.2A plus 0.45B equals 0.3. Okay, but it's 30% of what? Okay, you got to answer that question. Okay, so are you guys good to solve it from here? Again, substitution, elimination, whatever floats your boat. Okay, that's it for today.